In this lecture video, we are going to finish up the last part of chapter section 6.1, which is going to include the exception to octet rule and also the Lewis structure of organic molecules. Okay, so the paper homework that you see here is posted on Moodle already. There is the drop box for the homework that you can drop in. So just go to the homework chapter 6 part 1 section and then click on paper homework chapter 6.1, okay, to access to this document here. So the exception to octet rules you see a little bit in the previous lecture video when we talk about the sulfate. So I'm going to elaborate more onto that. So the exception to octet rules, there are three things that can be the exception. The first one is the odd electron species. Odd electron species refer to the molecule or ions that they have the overall or the total number of electrons to be an odd number. And we call this free radical. This type of molecules are going to be very reactive because they don't have the electron in pair. They have like one free electron, which is what we call free radical. So they are very unstable and also very reactive. So in nature, you are going to see this. They are not going to have a long life in nature. They are going to like tend to react with other species very quickly. So an example of this is the chlorine monoxide here, ClO. Okay, so this is not I, this is Cl. So if you count the total of valence electron, it's going to come out equal to 13, right? So 7 from chlorine, 6 from oxygen. And if you try to make the Lewis structure or draw Lewis structure, you are going to get the chlorine connected to oxygen, and you are going to end up surrounding these two element with the rest of the electron, right? So total have to add up equal to 13, right? So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. Okay, so that's only have 7. The reason why it is okay to have only 7 because we have the total number of valence electron only 13. You cannot have more than that. So that's why this would be one of the exception to octet rule. It can have less than 7 because we don't have enough valence electron to give oxygen for that, right? So now you might ask me, hey, why do we give chlorine 8 but only 7 for oxygen? What about if I give oxygen 8 instead and then 7 for chlorine? Would that be possible? The answer is yes, right? So as long as you have the same connectivity, different location of electron, we actually call this what? Resonance structure, right? So these two are resonance structure of each other according to the previous video that we discussed. Now, what if I convert some of these lone pair into double bond or triple bond? Would that be possible? So you are welcome to do that too, and we are going to talk about whether it's possible or not, right? Cool. So pretty much I'm going to convert one of these lone pair, okay, into the double bond. So I get rid of this lone pair, add to the as double bond. Okay, so that's one possibility. Another one would be get rid of pretty much like the lone pair of oxygen, right? Actually one of these, and also get one of these, right, to make it to be double bond. Okay, so that's another possibility. Again, the overall have to come up equal to 13 because that's the overall we have, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So that's good. Okay, what about this one? Would this be possible? Okay, so let's try it. Okay, so we're gonna analyze this later, so I'm just gonna draw it out. Okay, so pretty much we're gonna add triple bond, so you need to reduce those lone pair, right? So everything will be the same. So in this case, you need to make sure that the overall have 13 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So that's good. Okay, so since we have one lone pair here, so I'm just gonna swap the place, right? So total number of electrons still gonna be 13. Okay, so which one would be the best then? Okay, so this is when you will need to look at the possibility of how element can hold electrons. Okay, so for oxygen and chlorine here, oxygen wouldn't, so this one, if you count the number of electron around this oxygen, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9. So this oxygen has more than an octet. Okay, so it's have exceed octet. Oxygen cannot have an exceed number of 8 electrons. So that means in this case, all of these are incorrect. okay, because they exceed the octet rule. Okay, they have more than 8 electrons, including this chlorine as well. 1, 2, 3, 4, 5, 6, 7, 8, 9. Right, so that means in this case these four structure are invalid. Okay, so they are not correct structure because it exceed the octet. Okay, I know that there is the exception to exceed octet, but we're going to talk about those later. But know that oxygen is not going to be one of them. Okay, so and chlorine that is not as part of the central atom is not going to be one of them either. So that means these are going to be invalid because some of these elements in each of these molecules, those have more than 8 electrons around it. Okay, so that means I can get rid of these 4. So now between these two candidates, which one do I know should be the most important one, right? So this is, since these two are resonance structure of each other, right? Because we have the same order, the only thing that we have it different is the location of electron. Okay, so again, when I'm talking about the resonance structure, it have to be coming from the valid Lewis structure. This invalid Lewis structure is not part of resonance structure. Okay, so it just literally means that this is not usable, right? It's incorrect, period. Okay, these two are correct, but there will be one over the other that is more important or the most important, and that is when we will use formal charge to determine that. Okay, so in order to use the formal charge, you need to use the number of valence, right? So chlorine has 7 minus the unpaired electrons, minus the lone pair electrons, 1, 2, 3, 4, 5, 6, right? 7 minus 6 equal to 1. 1 minus number of bond equal to 0, right? So do the same thing for oxygen as well. 6 minus 6 come from valence of oxygen, minus 1, 2, 3, 4, 5. Minus 5 equal to 1, right? Minus 1 more, which is 1 bond, is equal to 0. Okay. Do the same thing for the other one. You are going to get 1 and negative 1. Again, this is neutral molecule, so the overall come out equal to 0. But the best or the most important structure would be those structure that each of the atom within the molecule has the formal charge closest to 0, and is indicated that this structure right here has the formal charge closest to 0. So this is going to be the best Lewis structure or the most important Lewis structure among these two. Okay, so again, it's not necessary to have an octet here because what we have is only 13 electron total. So therefore, in this case, we do not need to put extra electron because we don't have enough. Okay, so that means in this case, oxygen doesn't have to meet an octet because of that. Okay, so that would be the odd electron species. The second exception to octet rules is going to be the incomplete octet. Okay, so the incomplete octet refer to the central atom. Note that I highlight this, right? So every time I'm talking about it, is going to be the central atom that we are focusing on. The central atom do not need to have an octet. If the central atom is either beryllium, boron, or aluminum, so it's one of those. Okay, they don't need to have to meet an octet. Why is that? Okay, so this is have to come out with the number of valence electron total again. So beryllium is in group 2 plus 2 valence electron from hydrogen. That is going to equal to 4. So if you draw Lewis structure, so beryllium would be in the middle, right? So hydrogen have to be the terminal element. You are going to see that we already spent 4 electron, right? So we already spent that. So it's 1, 2, 3, 4. You already have 4 electrons to spend. You already spend those in 2 bonds. So therefore, in this case, this is going to be the Lewis structure of beryllium dihydride, because we don't have enough electron to spend to make beryllium to have 8 electrons. So that means this is going to be the correct Lewis structure for that. Okay, same thing for boron trihydride as well, right? So you have 3 from boron, 3 hydrogen, and total would be 6. So in this case, if you put a single bond around boron to connect it to each hydrogen, you are going to end up spend 6 electrons anyways. So therefore, in this case, you will not need to have 8 electrons around boron, because this is how much we have for electron. We already use it all. Okay. Do not add any more electron, right? So you need to have overall electron equal to the number of total valence electron that you calculate. Same thing for aluminum too. If you calculate for aluminum, you are going to see that the maximum number of amount of electron would be 6, and already this structure already have 6 electrons. Therefore, in this case, aluminum would not need to have an octet. So this is what we call incomplete octet, because it has not achieved that octet rule yet. It's lacking the octet, but it is okay because the total number of electrons doesn't allow us to achieve that. Okay. All right, so the last exception is called expanded octet, which is going to refer to, again, central atom. When we talk about expanded octet or incomplete octet, we are focusing on only the central atom. Okay, so the central atoms that are the element on the 3rd row and beyond would be able to have the expanded octet. Okay, so what are those elements? Okay, so 3rd row and beyond would be that. Okay, so if any of these elements are in the center or are the central atom, they can have expanded octet, and we call the expanded octet, the molecule that can have the expanded octet, hypervalent molecules. Hyper mean like exceed, right? Valence is the valent electron. It's the molecule that can exceed, like the 8 electron here. Okay, so the reason for that is because they can use the d orbital to accommodate more than 8 electrons. Normally, if you're looking at row 1 and 2, okay, so you are going to see that this row here has only s and p orbitals. It doesn't contain d orbital, but when we talk about n equal to 3, right, that's when the when n equal to 3, that's when the quantum number allow is to have the d subshell. So that means in this case, the element in 3rd row and beyond can actually use their d orbital to accommodate more than 8 electrons. Okay, so if you think about it, right, so S and P, S can contain 2, P can contain 6, total would be 8. But if you want to have more than 8, you need to have d orbital, and the only row that can start the d orbital with is row number 3 and beyond. So that's why it's going to be this. Why didn't I circle any of these? Well, because right now we are focusing on molecular compound, right? We are focusing on the Lewis structure of sharing electron, which is the molecular compound which contain covalent bond. That's why I'm focusing on only the non-metal, okay? Because all of these would form ionic compound, which is the electron already transfer. Okay, so in this case, we are focusing on the Lewis structure of molecular compound that contain this non-metal. Okay, so this is the reason why, if you refer back to the previous video when we talk about sulfate ion, the reason why sulfate ion, sulfur can accommodate more than 8 electrons around it, right? So in the sulfate ion, you will see that it has more than 8 electrons. The reason for that is because sulfur has d orbital, has the accessible d orbital that can accommodate more than 8 electrons around it. So that's why sulfur can have more than that. We're going to see more example here. Okay, so another example is, for example, sulfur hexafluoride, right? So of course this, if you draw this, definitely there would be 6 bonds around sulfur. So of course it's going to be more than 8 electrons. The reason why it's possible because it can use the orbital to accommodate more than 8 electrons. Okay, so same thing for like phosphorus as well, right? PCl5 is going to have more than 8 electrons for sure. And same thing for those noble gases that can actually form bonds as well under extreme condition. For example, krypton, xenon, and radon. Right? So under extreme condition, these can form chemical bonds, which can form molecular compound, and those can also have expanded octet as well, or they are the hypervalent molecule. Okay, so what do I mean by that? Okay, so let's take a look at an example. So I have I3 minus, this is the iodide ion. Okay, so what we're gonna do is, I'm just gonna go ahead, right? So we see on the periodic table that iodide is in the 1, 2, 3, 4, 5, like 5th row on the periodic table. So that means iodide can have expanded octet. It's not going, we are going to take a look at that. Okay, so we're going to take a look at why it's going to have expanded octet. As long as the formal chart is going to, like if you have a good formal chart for that particular compound, if the formal chart come out and is indicate that it's a better formal chart, then it's going to lean toward one structure over the other. Okay, so and one of them might be the structure that have more than 8 electrons around it. So I'm just going to go ahead, write out the valence electron. Okay, so calculate this. 3 iodide, right, valence electron plus 1 because we have negative 1 as the number of electron that is accepting, right? So accept 1 electron, total would be 22. Okay, so I'm going to, because they are 3 iodine, right? So I'm going to put 3 iodine right there, iodine. And I'm going to connect them with the single bond. If I do this, I already spent 4 electron sharing, 1, 2, 3, 4. So I'm going to have 18 electron left. When you have 18 electron left, what you are going to do is make sure that the outer atom must meet octet first, which means that these 18 electrons need to be contributed to the outer atom first. Okay, so I'm going to distribute this 18 into the first iodide. So 1, 2, 3, 4, 5, 6. Okay, we already spent 6. Okay, so 7, 8, 9, 10, 11, 12. Okay, so we already spent 12 out of these 18. So we already spent 12. We would have 6 left, right? Because we have 18. So that means in this case, the leftover then will go into central atom. Okay, so how many left over? It would be 1, 2, 3, 4, 5, 6, right? Because add all of this together, it need to equal to 18, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, so make sure that you distribute outer atom first so that those outer atom meet octet, and then the rest of it will go to central atom. Okay, and not only that, you will need to also calculate formal charge as well. Make sure that this is a good structure, right? So use the bracket, okay, to indicate the overall charge, -1, and then calculate the formal charge. Formal charge for these 2 iodide would be 0, right? So 7 minus 1, 2, 3, 4, 5, 6, 7, equal to 0. 7 valence minus 1, 2, 3, 4, 5, 6, 7, right, equal to 0. Iodide contains 7 valence electron minus 1, 2, minus 2 bond, 3, 4, 5, 6, 7, 8, and total would be -1, right? So 7 minus 8, it would be -1. So therefore, in this case, if you're looking at this structure here, the formal charge already close to 0, and the -1 right here, if you add all of these together, is already equal to the overall charge that we want. So that means this is going to be the best Lewis structure already. Okay, so this would represent the best structure for this I3 minus. All right, and oh, sorry, and if you go back, the reason why we see this as expanded octet again, because this central atom has more than 8 electrons. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And again, this is okay because iodide is in below, is on the, what do you call it, like 5th row, right, that we just count. So it's beyond 3rd row that it can use the d orbital to accommodate the extra electron that is have. Okay. Now, the next example is PCl5. So what I would like you to do is, I would like you to draw a Lewis structure for this. Okay, so do the same thing that we did earlier. I would like you to write out phosphorus pentachloride for this. Okay, so let's pause the video, complete this problem, and resume the video again when you finish. All right, let's check your answer. So again, I'm going to start with looking at the location of phosphorus, right? So this is on 3rd row, and then chlorine is in group 7. So the valence would be 5 and 7, right? So add them together, all of the atom. So you're gonna get 40 electron total. And because phosphorus is only one single element here, and we have 5 chlorine, so I'm just gonna put phosphorus in the central, as a central atom, and then surrounded by chlorine. And I'm going to start with single bond first, right? So if I do this, phosphorus will already have 10 electrons, right? So around it, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that is okay because phosphorus can have expanded octet because phosphorus is on 3rd row, right? So that means in this case, I can do that just by doing the single bond, okay? And the next thing we're going to do is, we already spent 10 sharing, so we have 30 left. So where would this 30 electron left go? It's going to go to the outer atom first, right, to meet an octet. And if you have extra, that's when it's going to go into the central atom. So if I do that, I'm going to start with the first chlorine. So 2 electron, 4, 6, that's already spent 6, right? So another 6 here, that would be 12, right? So why is it only 6 electron? Well, because 1, 2, 3, 4, 5, 6, and then another 2 sharing, 7, 8, make the outer electron have octet, right? The outer atom have to have an octet. So that's already octet. If you do all of this, you are going to spend a total of 30 electron, okay? Then you need to check the formal charge as well. The formal charge, if this is the best structure, is going to be equal, like close to 0. So if you check formal charge, the formal charge for all chlorine would equal to 0. The formal charge for phosphorus will also equal to 0 as well. So that means this is the best Lewis structure that represents phosphorus pentachloride. Okay. All right. So the next example, I would like you to do the same thing. I would like you to pause the video and start to count the number of valence and draw Lewis structure. All right, so let's take a look at your answer together. Again, if you have not started working on this example yet, please do so. You will need to try to do it yourself first. If not, then you will not learn. Okay, so let's take a look at your answer. Okay, so pretty much SOCl2. Okay, so first we're gonna look at, right, so sulfur, and we have oxygen, and we have chlorine, right? So 6 valence, and chlorine has 7, and sulfur and chlorine is on the third row too. According to this, the number of valence would equal to 26 electron total. Which one should be the central atom? According to the previous video, right, the central atom would be the one that have the least electronegativity value. Okay, so that means the lowest value. And in this case, between sulfur and oxygen, because chlorine, there are 2 of them, is going to be sulfur. Sulfur has going to have the lower En value because sulfur is going to be bigger than oxygen, right? So it's not going to withdraw electron very well. So we're gonna put sulfur as a central atom. And I'm gonna start with single bond. Okay, so if I start with single bond, I already spent 6 sharing electron. So I have 20 left. Again, these 20 electron must be distributed into the outer atom first, so that these outer atoms have octet. Okay, so I'm gonna start with those. So it needs 6 more. Each of these would need 6 more. So I'm going to add those 6 electrons to those. And if I do that, I'm going to have 2 electrons left. That's gonna go into the central atom. If you look at this, you probably notice that the number of electron, right? So if you count around this, is going to meet an octet. This meet an octet. This also meet an octet. Sulfur also meet an octet as well. 1, 2, 3, 4, 5, 6, 7, 8. So it seems to be really good, right? Because every atom meet octet. Okay, so that means in this case, this probably be good. But wait a second, you need to calculate the formal charge, right? So if you calculate formal charge, it's going to come out equal to 0 for chlorine, and -1 for oxygen, and +1 for sulfur. So it seems to be good because the negative formal charge is on the most electronegative atom. So that seems to be all right. But wait a second, what if I, right, change the single bond on oxygen to be double bond? Would that be possible? The answer is yeah, because in this case, oxygen still have an octet, chlorine still have an octet, right? The only thing that have exceed octet is sulfur, right? Because right now sulfur has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it seemed to be valid because of these outer atom meet an octet, and sulfur doesn't meet an octet, but is part of the exception, right? Because sulfur is on the third row, it can accommodate more than 8 electrons. So that means these are the 2 candidates that we have. These 2 are what we call resonance structure because they are having the same order of element but different location of electron. Okay, so these 2 are resonance structure. But which one is the most important resonance structure then? That's when you will need to calculate formal charge. Okay, so if you calculate formal charge for the second molecule, you are going to end up with 0 for every element. So the formal charge of the second structure is way better than the formal charge of the first structure. Therefore, in this case, the most important structure would be the second one. This second one would be the most important structure, which is the most correct structure. that represent SOCl2. Okay, so because the formal charge come out equal to 0. Again, the reason why it is okay because for the sulfur to have more than an octet, because sulfur is on the third row element that can accommodate more than 8 electrons. Okay. All right, up until this point, you should be able to start working on paper homework 6.1 part D number 9, which is asking you to draw this Lewis structure of this part would be part of the exception to octet rule, which means that some of those elements doesn't need to have an octet. Okay, so, and those rules that we already look at, right? So one would be odd number of electron, the other one would be the incomplete octet, right? And the last one we just look at is going to be expanded octet. Okay, so that means this example here would fall into those sections. Okay, so start working on homework soon to reinforce your understanding. The last part of this lecture video is the Lewis structure of complex organic molecule. When I talk about organic molecule, what do I mean by that? Okay, so the organic molecule is the molecular compound that contain carbon and hydrogen. Okay, so organic molecule is the molecule that containing majority of it would be carbon, and it's also contain hydrogen as well. So an example of that would be this amino acid glycine right here. Okay, so it's contain carbon and hydrogen, right? So this is what we call organic molecule. We're gonna learn about this more in detail when we if you are taking 123, Chem 123, you are going to see more of this organic molecule later. But for now, we are just going to focus on how to draw the Lewis structure of this complex organic molecule. Okay, so the OO that right next to each other, please note that this is called functional group. Functional group is the one that is going to be the group that is indicate the property of that molecule. So this group right here is going to have the oxygen is actually connect directly to carbon, double bond to carbon. This parenthesis here is indicate that this oxygen going to double bond to this carbon, okay? And this carbon going to actually bond with this oxygen right here, okay? So what do we mean by that? Okay, so let's take a look at how to draw it. First step would be the same, count number of valence. You are going to count each of these, right? So 5 plus 5 times 1. 5 come from 5 hydrogen, right? 1 is from hydrogen, so 2 plus 1 that's equal to 5. We have 5 hydrogen. Each hydrogen contains 1 valence electron. Okay, so plus 2 times 4 because we have 2 carbon. Each carbon contains 4 valence. And then you 2 times 6 because we have 2 oxygen. Each oxygen is 6 valence, right? So total would be 30 electron. So what do I do next? Okay, so the next thing you have to do is still going to be the same. It's still going to be the same process. You need to find out the skeleton. Remember, hydrogen need to be the terminal element. According to the organic complex molecule, pretty much the order of these would be the same order that is given. So it's going to indicate that somehow hydrogen would connect it to nitrogen, right? And so on. So nitrogen is going to somehow connect it to those 2 hydrogen because these 2 hydrogen have to be the outer, right? So the terminal, because hydrogen cannot have more than 1 bond. So that's why I have to put it outside. And it's going to force us to connect nitrogen to the next carbon, right? And it's also indicated that this hydrogen right here need to be outside also because hydrogen cannot have more than 1 bond. Okay, so that's going to leave this carbon to connect with the next. Okay, these parentheses that I just mentioned is indicated this oxygen is going to be separate from this oxygen. Okay, so that means I'm going to have to separate this oxygen out. Okay, and this carbon right here is also going to be forced to connect to the next oxygen. And this oxygen contains hydrogen, right? So that would be the skeleton that you will need to derive first before you do anything else. The next step would be the same. What you need to do is start with single bond. Okay, so start with single bond. If you start with single bond, you already spend how many electrons? You need to know as well. Each single bond contains 2 electrons. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 electrons. Therefore, we spend 18 electrons total in the sharing bond, right? So how many we have left? The leftover is only 12 electrons. as we did earlier, right? So you are going to distribute these 12 electrons to the outer atom first, right? Because the outer atom must meet octet. Okay. If I look at that, these 12 atoms, you can put it in 2 of them in nitrogen, right? Because on nitrogen, because nitrogen has only 6 plus 2 more, that would be 8. That's good. And then I'm going to start put it on oxygen, right? So if you do that, you are going to end up having how many electrons spent now? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We already spent 12 electrons that is left, which is good. However, if you check this is not going to be valid Lewis structure yet. This is incorrect Lewis structure. The reason for that is because carbon contains only 1, 2, 3, 4, 5, 6. It has only 6 electrons. It doesn't meet an octet yet. And of course, carbon is not one of the exceptions. So you have to have carbon to have an octet. Okay, so therefore in this case, you will need to somehow add double bond. Okay, so you can add double bond by, so pretty much I'm going to move this lone pair right here and make it to be double bond. Okay, so you can do that as well. And the next thing you need to do is check formal charge, right, for all atoms. So all hydrogen would be 0, nitrogen would be 0 as well, carbon 0, oxygen 0, this carbon 0, and this oxygen is 0. So this molecule right here contain formal charge of all atom equal to 0, like closest to 0, right, or equal to 0 in this case. So therefore, this is the best Lewis structure already. Okay, so this would be the Lewis structure that describe glycine amino acid. Okay, so if you don't know how I calculate formal charge, again, go back to video chapter 6.1 part 1. I already went over how to calculate formal charge for that. Okay, so now the second one is going to be a little bit bigger, but the skeleton is already given to you. On the exam, you might be given something like this as well. If I give you the skeleton and I ask you for the Lewis structure, you should be able to do that as well, right? So it's similar to the previous example that you need to come up with your own skeleton. The process is still going to be the same, except this one is already giving you a skeleton to start with. So that is a little bit easier. One thing I would like you to do is on your lecture manual, there is extra bond right here. Can you get rid of that? Can you erase that, or can you cross it out? Okay, if you cross it out, it's going to actually look like this. Okay, so this is actually the correct skeleton that I'm giving to you here. You are going to do the same thing. Okay, so first step, count number of valence. If you count number of valence, you need to know the chemical formula first. Chemical formula of this is C4H5N3O. How did I get this chemical formula? Well, all I need to do is just count them, right? So there are 1, 2, 3, 4 carbon. We have 5 hydrogen. We have 3 nitrogen, and we have 1 oxygen. That's what the chemical formula coming from. Is coming from this structure. So after you know this, then the next thing is count the number of valence electron by add of those together, right? Of this valence electron together, you're gonna get 42 electron. Okay. Since you have 42 electron, the next step, normally you will need to write out the skeleton, but since this is already given, right? This skeleton of the DNA and RNA base, which is cytosine here, is already given. So that means in this case, we don't have to come up with our own skeleton, but we are going to use this skeleton to complete the rest of the Lewis structure. So we're gonna do the same thing. Normally, you are counting the number of valence. You write the skeleton, then you count the number of sharing electron, right? And see how many electron left. We're gonna do that the same thing too. So we're gonna count the number of sharing by counting the number of bonds that is already pre-exist on this structure. So if I do that, I'm going to count that's equal to 1, right? 2, double bond. If you see, right, each of these bond contain 2. Since you have double bond, total would be 4. So this is 4 sharing electron. Double bond contain 4 sharing electrons. So 4 already, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. So we already have 28 electron in sharing bond. Okay, in sharing in the bonds. Okay, how many we have left? We are going to have 14 electron left. Again, how do you distribute this 14? It's going to have to go to the outer atoms first to make sure that they have made an octet, right? So I'm going to give oxygen 4 more so that this oxygen have an octet, right? So 1, 2, 3, 4, 5, 6, 7, 8. Okay, we have 10 more to go. Okay, so I'm going to put the rest of that into the outer to the central atom now. Okay, so we're gonna put 2 into this nitrogen because it's contain 1, 2, 3, 4, 5, 6, 6 only, 7, 8, right? And then put 2 into this, right? So 1, 2, 3, 4, 5, 6, 7, 8. Now it's have 8, and then the other 2 would be the last nitrogen. Total of all of these, if you count them all, the electron in the bonding and the electron in the lone pair of these together, it need to equal to 42. But wait a second, I actually have not used the other 2 yet, right? So it's going to be in this. I'm going to put it in this, right? Because right now the leftover is 14. So how many do I spend now? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yeah, okay, so I already spent that 14 electron. Okay, so the next thing is you are going to make sure that every atom, especially carbon and nitrogen here, they cannot, carbon, nitrogen, oxygen, they cannot have expanded octet. They have to meet an octet. Carbon, nitrogen, and oxygen need to meet an octet. Therefore, in this case, we need to make sure that all of those atoms have an octet. Okay, so this hydrogen already have an octet, same as for this oxygen, same as for this carbon, right? This have an octet, this have an octet, this have an octet. The only 2 that did not have an octet would be these 2 carbon, right? Because it contain only 6 electrons. What do I do? Okay, so this is when you will need to start making double bond. Remember, if you use every electron already, the next thing to do is to add double bond. Okay, so to add double bond, you need to get rid of 1 lone pair. So pretty much, I'm going to add double bond right here, right, to get rid of 1 lone pair. So now carbon have an octet. This nitrogen also have an octet as well. That's good. Now between these 2 carbon, I'm going to get rid of this 2 lone pair, right, to make it double bond. So now these 2 carbon also have an octet as well. To make sure that this structure is actually the most important Lewis structure, you are going to calculate the formal charge. Okay, so if you calculate formal charge for all of these elements, you are going to see that they all come out equal to 0. Okay, so this is going to be the most important Lewis structure for cytosine, which is the main base found in DNA and RNA. Okay, so up until this point, you should be able to start working on chapter 6.1 homework, part E, number 10. Okay, so there are 3 structures that is given to you here. Okay, so pretty much note that you have 6 carbon, right? This is the Lewis structure of organic compound. Again, why is it called organic compound? Because it contains carbon and hydrogen, right? So these 3 are called organic compound. So pretty much you see 6 carbon and 14 hydrogen. Note that hydrogen have to be the terminal atom. Therefore, in this case, you are going to pretty much connect 6 carbon together, right? And then surround them by hydrogen. Okay. For this one, same thing, you are going to surround this carbon by hydrogen, and then it's going to force you to connect to oxygen. Okay, so this oxygen connected to hydrogen, so that would be the skeleton. And you see the parenthesis oxygen here again. So note that this parenthesis oxygen is not connected to this oxygen, it's actually connected to the adjacent carbon that come before that, right? So that means in this case, the skeleton would be carbon, carbon, oxygen, and then this carbon connected to another oxygen. Okay, so similar to what we see in the previous example. All right, so this video pretty much we talk about the exception to octet rules, and we also look at the Lewis structure of the complex organic molecule as well. So up until now, you should be able to start working on homework 9 and 10. And because you already watched all 3 parts, so pretty much you can actually finish the whole thing. Okay, so make sure that you submit this on Moodle. There is the Dropbox part on Moodle that you can submit this, and the answer key will be released to you. Please submit it before the deadline, because once I release the solution, I will not be able to accept any late homework anymore. So you are going to end up with a score of 0 if you are submitting after I release the paper homework solution. Okay, so you are responsible for checking your answer against the solution as well, and address any question with me. And your paper homework will be graded based on completion and also your work as well.